welcome back. We've got now the formula, let me show that again, for finding exactly out of n trials, x successes for some probability. It's a bit of a beast to calculate. Ultimately, though, if you are good with factorials, if you are good with your calculator, you can crank these out pretty consistently, pretty quickly for a single value, right? It gives you exactly x out of n, probability of exactly x successes out of n trials. That's all it will give you. So if you need at least x successes out of n trials, you would then have to repeat that calculation over and over again until you hit the maximum n out of n. Now, there's some shortcuts there. You could use technology. In Excel, there is a command, binom.dist, for binomial distributions. And if you use true as the final argument in your command here, it will give you the cumulative probability of having 0 to x successes. So it will not give you x or more, but you can get the complement of that or something like that. So you can get there with the binom.dist command. Alternatively, you can get exactly px, x successes out of n trials, using the false flag on the binom.dist command. So that's how we get around all that. Now, let's actually look at all of the possible outcomes here. And we're going to be a little more general here. So let's say that we want to do 10 trials. And each of those trials has a 2 in 3 probability of success, or a p-value of 0.67. So my question to you is, what is the probability of getting every possible outcome? So what's the probability of getting 0 out of 10 successes? What is the probability of getting 1 out of 10 successes? What is the probability of getting 2 successes out of 10? What's the probability of getting 3 successes out of 10? All the way up to what is the probability of getting 10 successes out of 10? If you did this by hand, which you have the right, you could plug in each of those values, 0 through 10, in for x. So you would do this a total of 11 times. N, of course, is 10. P is 0.67, and Q is 0.33, right? It's the complement of that. So you would do that 11 times. Or conversely, you could also use Excel with the false flag for these 11 values of x. So you do this 11 times. N is 10. P is 0.67. And if you do that for this set, you can give it a run, at least for a couple of them, come back and check on me. This is what your probabilities for each outcome should come out to be. You'll note that at the extremes is pretty unlikely, right? 0.0000153, I think that was enough zeros, for getting nothing. It's theoretically possible, but very unlikely. Also, if it's a 2/3 probability of success, you would expect that you get about 2/3 of them successful, right? So that's about 6 or 7. You'll notice that 6 and 7 are our likeliest outcomes, 7 the most likely, because again, 6.7, the expected value does round up, I guess, if we're rounding to the nearest integer. So that's where most of our outcomes are, but everything is possible. Each of those calculated individually, that's great. But wait a minute, this is a nice table. It's a distribution of how all of these outcomes are probable. So we got a probability distribution. We can turn this into not just a table, we can also turn it into a graph. So this is what that same probability distribution looks like when graphed. I've got my probability at percent value, right, in decimal form. I've got my number of successes from 0 to 10. And this is what it looks like. And note this kind of bell shape going on. That's kind of cool. I'm sure there's something I'm going to get on with that in the next few weeks. Here's a link to it. Let me try and pull this up, see if it works. It might. Yeah, so you can play around with this, see what's more or less likely as you change your relative probabilities. And no matter what your probability, there is a bell curve shape going on. That's pretty cool. But I digress. These binomial probability distributions tell us that if we do multiple sets of trials, our mean expected number of successes is NP. That's just expected value from previous courses. And the standard deviation, which is going to matter in a few weeks when we start looking at normal curves, we can also calculate as a square root of NPQ. These shortcuts is only true for binomial probability distributions. So don't think there's the divine truth of the universe, but they are pretty useful. Thanks.